So our next speaker is Anka Rodweeks from UCL. And I have accidentally started going. There we go. I think it's paused.
I think so. It's not moving now. Okay. Yeah, if it plays, I'll just try to keep time. But hi, I'm Anka Rodweeks. I'm a final year grad student at UCL, just south of London in Mullard Space Science Laboratory. Thanks to the organizers for all of your hard work, getting this conference running, despite all of the stuff that's going on, and also for having me here to talk about the galactic context of the Radius Valley. I've worked alongside a bunch of collaborators who are on the screen, and probably some I've forgotten to, on this work throughout my PhD. And you saw some previews of my work from Dan's talk earlier, so I'll talk to you a bit more about that in detail as well today. So I like to start off when I'm talking about the galactic context of planet systems with looking at them in the galactic plane, essentially looking at the LMB coordinates. This isn't quite all of the exoplanets that we've discovered, but it's a fair few of them, and they're color-coded here just by heliocentric distance. And yeah, what I really like to take away from this is that exoplanets are everywhere in the galaxy now. We found them pretty much everywhere, and so not only are we thinking about knowing thy planet by knowing thy star, we're also trying to, as someone said earlier, I can't remember who, we really need to know the galaxy as well. And the reason I mention this is because I'm going to be talking a bit today about planets around the Radius Valley in the context of the galaxy. And so the Radius Valley has been talked about a lot. This is an adapted plot of the Van Allen 2018 paper. And just to clarify, throughout this talk, when I talk about sub-Neptunes, I'm broadly referring to planets above the valley that have atmospheres. And super-Earths, I'm referring to rocky planets below the valley that do not, we believe, have significant atmospheres. So just to clarify the nomenclature of my talk there. And so I'll start off by talking about those planets that don't have atmospheres. So we think that they've been stripped away by various different theories, but essentially they don't have extended atmospheres, and they're a pretty simple two-layer model that you can think about these planets from the lens of. And the reason that I started with these planets is because you can see that we model these planets as having an iron core, a dense iron core, and a less dense magnesium and silicate, for example, alpha element mantle. And those of you who are interested in galactic archaeology, which I assume quite a lot of people are here, may notice that these elements are pretty similar to the elements that people use to model stars. And we want to ask the question, do these elements that we know vary over the galactic timescales, do they link to elements in the galaxy when we consider them in planets? And just as a really brief cartoon of galactic chemical evolution that I usually show at purely exoplanet conferences, so it's really great to be at a conference where everyone cares about stars and planets as well. But yeah, because of nucleosynthesis processes like type 2 supernovae, type 1a supernovae, and just generally stellar feedback processes, we think that alpha over Fe varies pretty significantly over the galactic timescale, and for various different reasons, this actually probably is a better tracer of the age of a star than just the pure metallicity. And so, yeah, stars that were born earlier in the galaxy, so on this diagram I'm showing time linearly traveling across the x-axis, and 0 is on the left-hand side here. So stars that were born earlier in the galaxy had a higher ratio of alpha elements in their chemical compositions compared to iron, as many of us know. And that means that younger stars that were born more recently, probably have more iron with respect to alpha in the disks that surround them when they're formed, that form planets. And so we want to ask, did the galactic context of these stars linked to the planet properties? And Adebakian et al. In 2021 answered this in terms of the chemical composition of these stars, as did Casey Brinkman's recent paper, maybe with slightly different results. But the broad understanding from the Adebakian paper was that this y-axis, the Earth-like normalized density of small rocky exoplanets, does in fact seem to correlate with the chemical composition of the star when you consider alpha and iron peak elements. And so we tried to look at this by homogenizing the host star parameters and looking at a few different host star parameters for a similar sample to this. And the way that I did it is it's really nice that I'm following Jamie's talk here, because we do use modeling in a similar way that has been discussed by a couple of different talks. And so I'll just run you through quickly how we do it. We use purely Gaia parameters as our inputs for this work. So that's how this work really started. We used Gaia photometry, corrected parallaxes, corrected metallicities from Gaia spectroscopy. And we used BASTA, the Bayesian stellar algorithm, to fit to GARSTEC models. So that was one of the lines on one of the plots that you showed there. That's what we use. And we use different grids of models for stars that we think that have diffusion in the core. And we think that we treat all of the interior microphysics as well as we can for this type of star. And from this, we get the physical stellar parameters and recalculate the planet parameters using the semi-amplitude K and the planet-to-star radius ratio to get the density and the composition and answer the questions. How dense are these planets? What's their composition? And how did this potentially link to stellar parameters? And in this case, I'm really interested in the distance and the age of these stars. And in my paper that was on the archive last year, we found that we think that what we're observing in this mass radius diagram of exoplanets, so mass along the x-axis, planet radius along the y, and again, these are just planets below the radius valley, that age seems to be correlated with the average density, the bulk density of these exoplanets. So you can see here that planets that are below this Earth density line, these are tracks from Zhang et al., sorry that has been cut off at the bottom of my slide there. Planets below that Earth-like density seem to be orbiting on relatively younger stars than those planets that are above that Earth-like density line. And I will highlight here that when we're talking about young and old ages, the range of ages are from 2 to 14 gigayears, so not super young stars in this sample, because it's very hard to do that with isochrones. And I just want to mention that we are populating this, population a bit more. So I've got another paper coming out soon, which adds a point to this diagram that has determined the stellar parameters of one of a new star that's hosting a planet in this regime with astroseismology. And there are 4 other stars in this sample that also have astroseismic constraints that we feed into our homogeneous stellar parameterization. So there's about 5 at the moment. Hopefully with Plato and future missions, we'll be able to increase the sample size and do some more astroseismology on these planets. But yeah, that'll be coming out soon too. And yeah, coming back to the original result, what we do is interpolate these planet compositional tracks, plot them as a function of age, and we think we treat our error bars as completely as possible in this work. So they look reasonably large, but even when you take that into consideration and do a Bayesian linear fitting, we do still get a significant statistical correlation between the ion mass fraction of these planets and the stellar age over galactic timescales. And so what we think this means is that younger stars tend to be hosting denser rocky planets, so those are the stars over on the right-hand side of this plot, hosting those rocky planets with larger cores, larger iron cores that might be formed because there's more iron in the disks of those stars. And the inverse is true for those older stars that are on the that are on the left-hand side of this. And yeah, like I said, you can go read that paper, and I'm happy to talk about it more if anyone wants to chat. But now I wanted to talk briefly about some similar work I've done on the planets above the radius valley. So now we're talking about planets that do have an atmosphere. It's much harder to model these planets because there's much greater discrepancies in the way that we calculate the densities because of the way that we model atmospheres. So it's harder to imagine exactly how such a trend would present itself in this type of sample, which is why we dealt with the rocky planets that we understand a bit better first. And so yeah, we wanted to ask whether this links to these elements in the galaxy too, now that we're adding on a hydrogen and helium envelope into our understanding of these planets over time. And the answer is we can't really see a similar trend in the Neptunes. And this might be because actually a lot of models for the sizes and compositions of sub-Neptune-like planets are really temperature dependent. And we're not taking that into consideration when we just plot it in mass, radius, space, and color code by age. But what this does tell us is that perhaps because we are seeing this trend, this galactic-linked trend in the small rocky exoplanets, it does point towards a true galactic origin for that trend because we're not seeing it in the sub-Neptunes. And so what we can do now, once we've homogeneously determined ages for this sample of rocky exoplanets and sub-Neptune exoplanets that have masses and radii determined. So it's not all of them, just the ones with the masses. We can compare the age distributions of the two populations above and below the radius valley. And this is really important because I think our understanding of how the radius valley forms, as people have mentioned in a couple of talks this morning, is really tied to their evolution, and this happens over different timescales depending on which formation mechanism you're dealing with. And so one way to do this, which has also been mentioned, considering the ages of exoplanets, host stars, is looking at their kinematics in the galactic context. So you can have a look at the isochrone ages, but you can also have a look at something like this, the tumor diagram, which many of you will be familiar with. But just to simplify things, to a very, very rough approximation, things inside this golden ellipse are thought to be maybe in the thick disk, which formed much earlier on in the formation of the galaxy and has much more iron-poor stars. And the thin disk is closer to the zero in this tumor diagram. And what you can see is there's really very few super-Earths with respect to sub-Neptunes in this thick disk area of this parameter space. We still need to do some work in fully interpreting this result and understanding whether there is a significantly different age distribution for planets below and above the radius valley. And we do need to try to increase this sample with missions like Plato in the future and HWO as well. And hopefully, within this year, a catalogue of host star parameters that include these sub-Neptunes and these super-Earths, and also host stars of planets that don't have masses across the whole diagram, the period radius diagram of known exoplanets will be released using fully homogeneous Gaia inputs and using our homogeneous stellar characterization. And that will be made public, and we'll be able to do some more analyses like these using homogeneous host star parameters. So I'll thank you for listening there. I'll leave my conclusions up. More dense super-Earths tend to orbit around younger stars. We don't really see the same thing in sub-Neptunes, and hopefully we can begin to really explore the differences between age distributions of exoplanet hosting stars with astroseismology from current and future missions. Thanks so much for listening.
Great talk, really cool results. We have time for a couple questions. One over there.
Hi, great talk, thank you. My name is Dom, I'm from the University of New Mexico. Do you think, maybe I just missed this, but do you think that metallicity plays a role in this as well, or not really?
Yeah, so I think metallicity in terms of measuring the average FE/H of these stars and putting them as a function of planet parameters. I think the reason that this work hadn't been done until the past couple of years was, one, because there were limited planet masses available in this regime, but also because we weren't seeing as strong of a trend between just bulk metallicity, the FE/H, and small planet parameters in the same way that we have been in the giant planet parameter space for a really long time. In this work, we don't see a correlation that is nearly as significant between FE/H and planet properties compared to what we do with age. And so when we thought about the implications of the results a bit more, I think really what we expect the cause to be is galactochemical evolution, but using the alpha Fe in addition to the FE/H, in order to characterize, where in the galaxy and in the galactic history the star was born. So probably a mixture of the two, and probably we need much more detailed abundances and spectra for these stars than what we can get from Gaia. To answer that, thanks.
Hi, very interesting talk. Just to clarify, so your argument for super-Earths being denser around younger stars is because there seems to be more metals in the overall disk?
Yeah.
In that case, does this also translate to more planets around younger stars as well, or more rocky planets around younger stars compared to older ones, since you have more planet-forming material?
Yeah, that's a good question. We haven't done an occurrence rate study on this sample or in the same regime, but I think that would be a really interesting thing to do. I will say that, you could also potentially, after thinking a lot about this sample, I think what you could probably say is that you can expect a greater diversity of rocky planets or rocky cores around younger stars or stars that are in the thin disk, potentially, in comparison to the thick disk because of the amount of iron. And, I'm not an expert in planet formation, but I'm sure that you could make an argument to extend that to more planet formation as well. So it would be interesting to look at that, for sure.
Awesome. We'll have to end the questions here, but let's thank Ankarat again.
Thank you.